So, uh, today we will be talking about the conversion of voltage into current using operational amplifier. So, uh, if I assume that Vi is the input voltage and I/O is the output output current, then the output current should be proportional to the input voltage. The situation should be like this. The output current should be the function of the input voltage. So this is why we call it conversion of voltage into current using operational amplifier. So you can say conversion. Now this conversion can be brought in action by two approaches. And the first approach is uh, that's that's you have voltage to current conversion using floating load. This is the first technique of achieving a result like this. And there is another approach that's the same voltage to current conversion with grounded load. Now let's first draw this circuit for for this conversion by making use of operational amplifier. So we have an operational amplifier, and it has two terminals. One is non-inverting, another is inverting. We have the output, and here we have a resistance. Let's call it R1, and here we have another resistance. Now, in general, we used to call it as feedback resistance, but here we will call it load resistance because this resistance is directly connected to the output. Now, since this load resistance is not connected to any kind of ground, this is why we call this technique as floating technique. So using floating technique, we would try to evaluate the expression so that we are in a position to realize that the output is in the form of current when we are subjecting voltage to the given circuit. So what else we have is uh, we will ground this resistance, and from here we will have a signal. Now the voltage here I will call this Vi, and let's ground it like this. And we can choose the junctions here. Suppose this is my junction, and we can think of current here as IL, and here say the current is I1, and here the current is Ix. So this is one situation. So if we think of this junction, if I make use of KCL at junction P, what's going to happen? I can have uh, I can have uh, I can have this IL equal to I1 plus Ix. Now we understand that the input impedance of the operational amplifier is infinite, so we can immediately say that the current flowing in this direction, Ix must be equal to 0. So we are left with the equation IL equal to I1. Right. So now let's proceed and write down this equation in terms of voltage and resistance. So what we are going to get there is, let's call it 3. So we have here, we can immediately think of this IL is V out. Let us assume that the potential at this point is say VB. Okay, here the potential is VA. So this will be VO minus VB divided by RL. It must be equal to I1. I1 is here. So what is I1? It is VB minus 0. So this is VB minus 0 divided by R1. All right. Now the point is that we can think of VB in this equation from this side. If we see VB, okay, what we have VB in terms of the virtual ground, this VB is equal to VA. And this VA is equal to VI. So we can immediately think of V out minus VB divide by RL is it is VI by R1. So here we have V out minus VB. Okay, now instead of I think that the right choice here is not to write anything in the left side because this is simply IL. So I want to get my result in terms of IL. So this is IL. So so I think the result is out here that IL will be VI by R1. So we can see that the load current here, here is IL. This is your output current. So this load current is output current is proportional to input voltage. So we can see that that we can directly convert the input voltage into the output current by making use of the circuit that I have shown you here, right? So here we can call this as a converter which converts input voltage into the output current using the floating load. Now this RL is acting as the load resistance, and this RL is not connected to any kind of load. Now the second thing that we have to do is we have to go for another technique by virtue of which we can obtain this what's called as the output current will be proportional to the input voltage. So to do that, so now we will be discussing the same conversion in terms of with the grounded load. So we will be discussing with grounded load. What voltage to current conversion, right? So for this we have a stipulated circuit, and let me try to draw that circuit. This is our operational amplifier, and this is the non-inverting terminal, this is the non-inverting terminal, and from here we have a situation like this. Okay, so let me cross it here. Then we have the non-inverting terminal here, and let me move like this. We have another resistance here, and then let's cross it. Then I have another resistance here, and from here I will cross this point. Then I have the load resistance here, and we have the ground here, and from here we can think of another resistance, and then we have a ground here. Now the condition for this grounded load system is that all the resistances that we have here except this RL, they are equal. So this is R, this is R, this is R, this is R, and here we will provide the input voltage. So this is the circuit that can be used to convert voltage into the current by making use of grounded load. So here we can directly see that this load resistance is grounded. So now in order to proceed, and we can think of the potential at this point as, say, for example, this is VA, and the potential at this point is, say, VB, and here we have the potential VI. So certainly we want to have a correlation, and and you can see the load resistance here. This load resistance is grounded. So that's the important point. Now if I have the current here, IL, okay, so here the current flowing is IL, and here I will take the current in this direction, right? So suppose this current is I1, and this current is I2. So we can think of KCL at junction P, and we can immediately write down an equation for KCL, and what will be that? That will be I1 plus I2 equal to IL, right? So at this junction we have made use of Kirchhoff's current law, and we have written down the equation for the currents. Now let's find the value of I1. So what should be I1? So this I1 should be, suppose this is VB, this is also VB. So we can write down here VI minus VB. Okay, so VI minus VB. What is the value of resistance here is R, and that should be clear. And then plus. Now what is I2? So this is output voltage. So it is V out minus VB, divide by R. That should be the case. And this is equal to IL. Okay. And now let us solve this. And we will have the LCM here. Okay. So this is R. This is VI minus VB plus V out minus VB equal to IL. This is the case, right? So we can have here VI minus twice VB plus V out divide by R equal to IL. So this should be IL, right? Now we want to use the result of non-inverting operational amplifier. Okay, we want to use that result here, and for that, if we can see where is the this is the non-inverting end, right? And we can make use of that result. And what's that result? That is V out is equal to 1 plus, it's basically RF by RI. RF here is R and RI is R. Okay, so here it should be VB. So V out should be, this R and R will cancel. This is twice V out. All right. So we can use this. This is VB. Sorry. So V out is 2 times VB. So I can think of this as equation 1. I can think of this as equation 2. So now let's use this second equation in equation 1. So using 2 in 1. All right. So what will be the result here? Yeah, this is VI minus 2 VB. Okay. So here instead of V out, I will write twice VB again, and divide by R is equal to IL. So this twice VB and twice VB will go, and we have VI equal to RIL. So we can directly see that the input voltage is proportional to the output current IL. This IL is the output current. So this way we have understood that how we can convert the input voltage into the output current. So we have made use of 2 approaches. One approach was in which we used the floating resistance approach. Another approach was the ground approach, and in both the cases we have seen that the input voltage is proportional to the output current. So this is the end of this this topic, the conversion of voltage into current.